Hi, this is Professor Fernandez, and this is video 1 in lesson 24. So in this video, we are going to talk about differentiating exponential functions. And you see 4 examples on the screen here from Calculus Simplified. So before going into those examples, which, these are all, if we look at them really closely, they're all either exponential functions or combinations of them, quotients, products. Let's go down here really quickly and just review what the derivative rule is for exponential functions. So this is theorem 3.8 in Calculus Simplified. What does it say? It says if b to the x is an exponential function, then the derivative of that is, well, let's take a look at what this rule says. It says, first of all, you take the exponential function and you just write it over. And then you multiply it by the natural logarithm of the base. So one specific thing, a special case that will happen here is, what if we are differentiating e to the x? So e here is Euler's number. This is, about 2.71-ish in decimal notation. So what if we differentiate e to the x, right? What do we get? Well, according to this rule, we write over e to the x, okay? And then we multiply it by natural log of e. So remember, natural log of e is log base e of e, and that is equal to 1. So this term here, while you can write it down, is actually just 1. So what we end up with is that the derivative of e to the x is just e to the x. Pretty simple. So in these examples we're going to do in a minute, there will be times when the exponential function we are differentiating is e to the x or some combination of that. So we won't have to write over this ln part, because as we just saw, that ln of e is 1 makes that part disappear from the derivative result. Great, so let's go back and look at these examples. Let me start with this one over here. I'm just scanning around for the simplest one that we could do quickly. Okay, differentiate 2 to the x. Well, like we just saw, the derivative of this particular exponential function, well, first we just write over the exponential function and then multiply it by the natural log of the base. So that's it. That's the derivative of 2 to the x. We can do all sorts of things with it. Surely we can find out where it's increasing, decreasing, analyze it in all sorts of ways, but we won't go there, right? This video is really just about using those derivative rules. Okay. I'm going to slide over here to the left and take a look at this next example. This one is a product of x with e to the x, so we're going to have to use the product rule. So if we differentiated g prime of x here, we are going to get the derivative of x times e to the x plus x times the derivative of e to the x. So that's coming from the product rule. X is a power function next to the first, so power rule. The derivative is 1. You could also think of y equals x is a line with slope 1, so its derivative is 1. Multiplied by e to the x here, and then plus x times the derivative we just calculated, right? So the derivative of e to the x is e to the x. And at this point, we can just factor out in e to the x, and we get 1 plus x. So that is the derivative result for this function. Okay, I'm going to scroll down over here. This function, h of t, is a composition of e to the x with x equals minus t squared. So if you want to think of it that way, that's the composition. So to differentiate it, we are going to write, to go a little bit slower here, f of g of t, and write f of x as e to the x, and g of t as negative t squared. So then, of course, we can check that f of negative t squared is e to the minus t squared, which is the function that we started off with, h of t. Okay, so then, again, that's just a quick little review, how you would identify the inner and outer functions. To differentiate h of t, then, we use the chain rule. So derivative of the outside, evaluated at the inside, times the derivative of the inside. And this is part of the reason that I wrote out what f and g are. So we're over here going to calculate these derivatives. Derivative of e to the x is e to the x. So that's what we just showed earlier. And derivative of g is negative t squared. It's a negative power function, so minus 2t by the power rule. Okay, and then now we just put all this stuff in the places it goes down here. So f prime of g of t, that is f prime of minus t squared, times g prime of t, so that is minus 2t. f prime is e to the x, so this is e to the minus t squared, and then times minus 2t. So our final simplified expression looks like this. Great, so I'm going to come back to this at the end of the video and show you a faster way to do it. The way that I did it here was meant to remind you of what the chain rule is, and then also get you used to just identifying composite functions and just following the rule. But I'll show you a faster way at the end of the video. Okay, so let me look now at h of x equals 3 to the x divided by 2x. This is a quotient function. So let's apply here the quotient rule, which says I'm going to differentiate the top multiplied by the bottom minus the top differentiated times the derivative of the bottom. All of that divided by the bottom squared. Okay, so in this particular setting, right, I'm going to have to use a couple of rules here. So first of all, in the numerator, I have 3 to the x. So keeping in mind that the derivative of the exponential function is the exponential function times the natural log of the base, that gets me that rule, a derivative result. And then the derivative of 2x, a couple of ways again, linear function, slope 2, derivative is 2, or using the power rule, the derivative here again is 2. Okay, and then divided by the denominator, which is 2x squared, that's 4x squared. Awesome. So at this point, I can do a lot of algebra to simplify this. And I'll just save a little time in this video and save you the algebra and give you the simplified form. So there it is, 4x squared. Okay, so anything else that, oops, excuse me, that is not a 4, that is a 2. Some of the algebra that I'm skipping in the simplification is that, there's a factor of 2 here that cancels out one of the factors here of 2 and the 4. Okay, so then, to end the video, let me go back and tell you what I said earlier about the simpler and faster way to do the derivative here. If you notice, right, this derivative rule is about differentiating b to the x, an exponential function. What if I wanted to differentiate b to the g of x? In other words, or I'll use u of x. This is how you might see it in a calculus book. In other words, the composition of an exponential function with some other function, like exactly what's happening here, right? So what would happen? Well, I would use the chain rule, right? I would say this is the derivative of the exponential function. So the derivative of, in this case, b to the u of x. The derivative would be b to the u of x times the derivative u prime of x. Okay, so where does that come from? So again, we can kind of derive this rule from considering, let's say h of x is b to the u of x. And h of x we can write as f of u of x, where f of x is b to the x. And then we can see what's going to happen by the chain rule. This is f prime of u of x times u prime of x. So u of x was, let's see, let me go back here. F prime of x, we need that, right there it is. F prime of x here comes from, you see it left over here, the rule for differentiating the exponential function, b to the x ln of b. So this quantity here would then be taking u of x and inserting it in everywhere I see an x, namely right there. So this becomes b to the u of x times ln of b, and then times the u prime of x, right? And that's good because it reminds me that over here, common mistake, you can see I'm doing it here, forgetting the ln of b. So erasing the stuff here at the bottom, so then we can go back and redo this example using this now faster way. How would we apply this over here? We'd say, oh, so this, oops, let me see, just meant to highlight this part. This is a composition, right? It's not e to the x, whose derivative would be e to the x. It's e to the minus t squared. So it's e raised to some other function of, in this case, the independent variable t. So the derivative of e to the minus t squared, and then notice again how this rule operates. Notice that this part, right, this is essentially the same thing as what we were being told to do over here when it was not a composite exponential function. In other words, write over the exponential function and then multiply by ln of b. Same thing over here, right? This is the exponential function form here. Write it over, multiply by ln of b. So I'll do that first. The derivative of e to the minus t squared, write it over, multiply by ln of the base. We won't need that in a minute, right? Because that's 1, but let's go back to the only other term that's here, right? This middle term, multiply by the derivative of the exponent function. The exponent function here is minus t squared, so I'm going to multiply by that derivative. So this is e to the minus t squared, ln of e is 1, and then over here the derivative is minus 2t, which gets us back to the same place we were at in the middle of the video when we did this example using the chain rule, but not using this new chain rule version of the derivative of an exponential function. Great. So I'm going to zoom back out here and just look at these. No other kind of general comments that I want to make other than, as you can see, this one required the product rule, this required the chain rule, this required the quotient rule. This one just required the straight up differentiation of exponential functions rule. So as with all these derivatives rules, they apply equally well to different families of functions, polynomials, rational functions, exponentials, and trigonometric functions. So this is one of the reasons why we in this course are leaving all of this for the end. This is lesson 24, right? Because at this point we've studied all those differentiation rules. So all we're doing now is we are applying them to different families of functions. Sometimes we get new rules like this one and like that one, but really they're kind of plays on old rules, right? So chain, quotient, product, things like that are still around, and we're still using them, as you saw in these 4 examples. Thanks for watching.